So now we're kicking off lecture 6. We're going to talk about regressions, but first some announcements. Okay, about the final exam. Most probably, or it will be held electronically, and which means that you will work with this at home, and I will try to keep the format as close to the last year's lecture or last year's exam as possible, and more information will follow. Remember, there will be no lecture this week on September 30, or we can say 30, okay, this week. Okay, so let's just get into it, okay? What you want to do, your ultimate goal is to make a forecast or a prediction from the data you have, and you remember that you had like a y variable and x variable, and you would your question was, how much will y change if x changes? Okay, and what will the level of y be on average given a level of x? Okay, and then you got like a regression line, which was your best guess. Okay, so in this lecture we will ask ourselves, what is the best model that we can build, and more importantly, what kind of statistical inference can we draw from this model? Because we're looking into the intercept and the slope, and we are going to look into how much confidence can we have in these parameters, such that we know whether or not we can use the model. Okay, and for the next lectures, lectures 7 to I think 10, we're going to look into multivariate models, where you have more than one explanatory variable. Okay, for example, x up until xn different variables explaining the y. Okay, but more on that later. The agenda today is just to set up the simple regression model, the SRM. We're going to look into theory, and we're going to talk about the inference of the parameters, the beta naught, or the b naught and b1, the intercept and the slope, and we're going to create some prediction intervals just to see the uncertainty in our estimate. And we're going to look into potential problems we might encounter, and that would be changing a variation in the data, like is y varying more or less based on the level of x. And we're going to look at outliers, which are points which do not seem to fit in with the other points or our regression model. And we're going to look into dependence among observations in time series data. Time series data is covered in the penultimate lecture, but it's extremely useful to use. Okay, and what we're covering today is chapters 21 and 22. So let's take a step back and look at the big picture. Okay, And why do we focus on regression models? And regression models, they are really the workhorse of statistical analysis. And they are everywhere. And if you pick a job, I'll give you a regression. So for example, if you do consulting, a question can be, how does competition affect price? So then you regress price, which is your y variable, on competition, which is your x variable. So whenever you wonder if something quantifiable affects something else quantifiable, what is the relationship there? Then you can use regression. And in marketing, if we increase spending on advertising by 10,000 kroners, how much would revenues increase? So then you regress revenues, which is your y variable, on spending, which is your x variable. And of course, like a first step is always to think like if the relationship should be like upward sloping or downward sloping. For example, for the competition example, how does competition affect price? Well, you could say that, well, more competition, the higher x, right, will lower price. Okay, because more competition, there's more pressure on the price. And for example, here in marketing, if we increase spending on advertising, would revenues increase? Yeah, probably revenues would increase because you get more customers. So here you get x and y, and probably you would get an upward sloping graph, right? Like a positive B1, a positive slope. And well, from finance, does a company's sales influence its stock price? Well, regress stock price, which is your y, on quarterly sales. And probably you would expect like a positive relationship here too, right? If it's linear or non-linear, we'll get back to that, okay? And of course, you already know how to deal with non-linearity. And often the average effect of y, the average effect of x on y is often quite important, and you can really or virtually find an unlimited number of examples of this, and that's why we use regression, because it's really a tried and tested method which we understand and which is simple to use, and that's what makes it powerful. And even if you're not going to perform these regressions yourself, you will use the results of the regression or of regressions, and that makes it really important to understand them. So we have a case study for today, and that would be Bucket Hansen. You're in the charge of deciding the location of one new store, okay? And you're considering a variety of different possible locations with different foot traffic levels, okay? And so this would be like pedestrians. The number of pedestrians, okay? So, does foot traffic affect sales? Okay, then you know that foot traffic would be your x and sales would be your y, okay? So one potential site has on average 40,000 people walking by per month, while another site has 32,000. So that would be like 1 person per minute. Okay. How much more can we expect to sell at the busier location? So this is actually where you use regression to make a decision, okay, and to make more money, right? So you have data for 80 locations, and you're assuming that these locations are the same given or based on price and based on neighborhoods. So you're virtually ruling out those two lurking variables. For each location, you have data from last month. So you have sales, that's your Y, and you have foot traffic, that's your X. So you regress sales on foot traffic and obtain a slope, B1, which gives you the expected change in sales given one change in X, okay, in foot traffic. So and you saw that in the last lecture. You found the slope of the regression, but now we're kicking it up a notch, right? So now we can look into how confident we are on that estimate. Okay, so how confident are we in this relationship in the B1, and what is the 95% confidence interval for the estimated slope, right? So how certain are we that this slope is, for example, different from 0? Because if it's not different from 0, then we could just take the average of Y and use that as our estimate, right? And what is the 95% prediction interval for the level of sales for a given location with 50,000 people, okay, walking by? So that would be a different analysis question or research question. But we can solve all these by looking into the regression model. So you did use the, as we said during the last slide, we did use regression in the last lecture, right? And we made like this regression line because we have some data with X on Y, or Y on X, and we just found the intercept and the slope, and we just said, well, we accept these parameters as true because they are describing our data. But now we're going to treat our data as just a sample from our population. Okay, so what does that mean? It means that every time we get some data, we just think that, well, we could just as easily have gotten a different sample, and we can take many samples from this population. So for every time you get a different sample, you get a different intercept and a different slope, right? So what we let's see where we are. So, yeah. Yeah, I think we mentioned that. Yeah. So, what we are looking into is to see what can our parameters tell us about the population parameters. So, we have the simple regression model, and these are the population parameters, right? So these are the population parameters, and we can't observe those, okay? What we can observe is the sample parameters plus E. So these are the sample parameters. Okay. So and you get the regression line is equal to the intercept plus the slope times x, okay? And the population regression line would be the beta naught plus the beta 1, the population intercept, and the population slope, which is not observed, okay? It's not observed. So what what can we tell about the sample parameters, okay? Based on our data, we can just assume a variation of the sample intercept and the sample slope. So let's continue in the next video.